Well, hello, Paul Russo here again, and today we're going to continue our discussion of light scattering and X-ray and neutron scattering. We'll begin with light, and what we say here applies also to X-rays and even to neutrons because, of course, particles have that wave-like character thanks to Dr. de Broglie. All right, so let's see if we can get going here. Here we go. Here is a sort of a picture of how light propagates through space. We speak in terms of a thing called the pointing vector, which is the purple arrow here. And this is where the light is going. It gives the direction of the light. And it can be thought of, light can be thought of as sort of leapfrogging of an electric field that's oscillating over a magnetic field that's oscillating. It's sort of like one kind of leapfrogs over the other. A couple things to notice about this. There is the wavelength lambda. We're interested usually in the strength of the electric field. Rarely do we talk about the strength of the magnetic field. And it's important to know that the electric field and the magnetic field have to be exactly perpendicular to each other. Okay? And so that vector cross product gives us the direction. One of the main ways that we have to quantify light, in addition to the strength of the electric field, is the spatial frequency of the light. Now, don't be misled here. Red and blue are both electric fields in this case, okay? So in the previous slide, blue was a magnetic field. Here, the blue is also an electric field. It's vertically oriented, just like the red light. But blue light is a little shorter wavelength than red light, and that's shown here. And what we say is instead of wavelength of the light, we often talk in terms of spatial frequency of the light. So we define a kind of a spatial frequency for each color. And higher spatial frequencies correspond to shorter wavelengths. Okay, so each wiggle corresponds to 2 pi radians of the light. And so anyway, the blue light has a higher spatial frequency or more wiggles per centimeter. I think this is puts that in a little bit more quantitative way. Typical numbers are shown now, and red would be maybe 100,000 radians per centimeter, and blue is maybe 130,000 radians per centimeter. It's not an enormous difference, and yet your eyes are, exquisitely capable of telling the one color from another, despite this fairly small difference. So another way to look at the spatial frequency that I like, anyway, is the number of rulings on a ruler. Okay, so one of these is the blue light, the high spatial frequency one. It's like a ruler with more tick marks, and the lower one is like the red light, and it's fewer tick marks on the ruler. It's not that the ruler is in metric here and in imperial units here. It really doesn't matter. It's just that there are fewer tick marks. This one is quoted out in 1/8 of an inch, and I guess that's 2.5 centimeters, something like that, maybe 3 centimeters, 3 millimeters, not centimeters. Okay, and so this leads us to, now that we understand spatial frequencies of light in one direction, we have to worry about the spatial frequency that really matters in a scattering experiment, which is given usually the symbol Q. As you look at other literature, you'll see people call it H, K. The X-ray diffraction people sometimes like S for this, and I apologize that there are just too many units, but it's like I'm always telling my wife, it's really not my fault. Somebody started to use these things. And it's a consequence of the fact that scattering applies in so many different fields that we have these different units, different people developed part of scattering theory. All right, so this is a quote from Ronald Jones. Nothing is harder to understand than Q, and Ronald Jones is a big deal up at NIST, and he was giving a talk at the same workshop on methods that I developed this scattering talk for. And I thought that was really very good. He talked only, I guess, really about neutron scattering, and I talked mostly about visible light scattering. Okay, so here's another way of looking at what Q can do for you. It's all a matter of detail, okay? Here's a soccer ball. It's a very shiny soccer ball with that reflection up there, but it's a soccer ball. And if you have a very long wavelength, and it turns out a very low angle, we'll come to that in a minute. But if you have a long wavelength, all you can tell is that, well, it's a soccer ball. I can't hardly see the details. On the other hand, if you have a very high Q, okay, then you can see right down to the stitches of the soccer ball, okay? And the scattering vector Q is sort of inversely related to the characteristic length that we can detect. So this Q thing is 2 pi radians over some distance d, okay? And so if all we can, in the low side over here, we're probing lengths that are, larger than the soccer ball, we can, if we're lucky, we'll tell there's a soccer ball there at all. And to the right side, we can see, into the stitching. So what it is, this scale Q, it's actually sort of the difference between the scattered light vector and the incident lights vector. So imagine that I will switch and actually draw this, and then maybe I'll get rid of it. Let's get a pin here. So I go out a distance along this scattering vector. There we go. There's a scattered K vector. And now I'm going to subtract the incident light vector. Okay? So that incident light vector was really up here, but I'm just going to subtract it and move it over there. And that's what gives me the scattering vector. It's going to work out that the scattering vector Q always bisects the incident vector and the scattered vector. So you can find it by that little vector subtraction thing I just did, or you can just say, okay, I'm going to draw a line right down the middle of where that one's going and where that one's going. And so you can see that if I have an angle here, which maybe looks to be on the order of 30 degrees, my incident vector, my Q vector is going to be oriented, oh, I don't know, maybe at 5 or something like that. And it works out that the length of this vector is 4 pi over lambda. Actually, that should be a lambda naught there. It really should not be. It really should not be errors in this presentation, but there are. So this should be lambda naught, which is the wavelength of the light in vacuum. And that's usually how we are quoted our laser wavelengths. So that's kind of a handy number to remember for your laser. So 4 pi over lambda naught, the wavelength of light, times n, which is the refractive index, sine of half the scattering angle. And then these here are vectors. Okay, you see this vector here. N is a unit vector that gives us the direction of the scattered beam and the direction of the incident beam. Okay, so anyway, you see that the spatial frequencies are sort of lower usually than they are for the incident light or the scattered light. So our characteristic despacing is indicated by these sort of gray areas here. And that's what we're probing. If we're looking at static light scattering, we're looking for differences in the system in the direction Q. And if we're looking at dynamic light scattering, we're looking for motions in the direction Q. And light scattering just automatically picks out that particular direction. Go to the next page. There we go. Well, I have a problem in this talk. Sometimes vectors get arrow on top. Sometimes they may look like this with an underscore. If it's not underlined, it means it's a magnitude. Just to remind you, vector dot products, A dot B is AB cosine of the angle between them. And so this is just a reminder a little bit about how vectors work, okay? And an admission that sometimes our notation isn't 100% consistent. All right, so light scattering really works off these phase shifts that arise between one ray of light and another ray of light that go through different parts of the sample. So let's pretend here, just for the sake of fun, that I have a little particle here, particle I, and another little particle here, particle J. Now these could actually be little subvolumes on the same molecule, or they could be little tiny particles that are totally different molecules. Okay, doesn't matter for this argument. All right, and so here I've put K as bisected the incident and the scattered ray, and I drew my vector K. And you can see that light going through the particle J has to travel a little bit longer. Okay, and so in doing that, it gets out of phase with light going through the particle I, right? So it could arrive completely out of phase, in which case there would be a destructive interference if the scattering power of particle I and J is the same, okay? So, but in many cases, it will only be partly out of phase, right? So the way to calculate the total distance is shown down here. I'll let you read that, but the total distance, the total phase lag, is the distance divided by 2 pi over lambda. And you can compute that as Rij, okay, the vector connecting I and J, dot producted onto Q. Okay, so this distance Qrij, phase lag is 4 pi Rij sine theta over 2 over lambda. Okay, and so you can sort of see how that goes. In this case, it's kind of an easy one. This one is a little bit more difficult to locate the particles where the phase lags occur, and I'll let you attempt that on your own sometime. This one I think is more difficult still because the difference between particle I and particle M is actually at a right angle to the Q vector. Okay. So I'll let you do this as a problem set. This is a problem. If you're taking this as a class, this is a problem set. Here we have Q is 4 pi, no refractive index, sine theta over 2 over lambda without the naught. So that actually does make sense. Okay, so the next thing that we're going to talk about is dipoles and what goes on and how scattering actually happens. And we'll use as our basis visible light. Okay, and I borrowed this little graphic from the people at Wyatt who sell us the light scattering instruments that we use. And what it shows is a red laser beam at a certain wavelength, going past a molecule. And the beam, the laser light is this oscillating electric field. Of course, it's moving at the speed of light, so it's going by very fast. And it corresponds to extraordinarily high frequencies. So we could calculate the frequencies of light. If the particle is standing still, the peaks and troughs of the laser light go by it at something like 10 to the 14th, 10 to the 15th cycles per second. So it really oscillates fast, okay? And so the molecule basically just sits there, and only its electrons are light enough to respond to those frequencies, okay? So it's sort of like if you to grab a tree and shake it, only the leaves will really move, right? The whole tree isn't going anywhere. So this is a particle. We'll just take this to be, even if let's just say it's a hydrogen atom, a single hydrogen atom. Well, I better have 3 charges. It looks like they have plus and minus. It's 3, so I guess it's whatever. Lithium. So it doesn't matter. The atom itself, the nucleus of the atom doesn't move, okay, not much. But the electrons, they jiggle pretty fast. And we write that there's a stimulated dipole, an induced dipole, which is given by the polarizability of the molecule times the electric field. Now, if you work out the units of this polarizability, and if you choose your units right, choose what are called ESU units, you'll find that this polarizability is actually essentially a volume, right? So this is, by the way, different from the polarity. All molecules have polarizability. Not all molecules have polarity. Even a completely non-polar molecule, let's say carbon tetrachloride, you can induce a polarized polarity to it with an electric field. And if you do that at a very high frequency like light, wave frequencies, 10 to the 14th, 10 to the 15th hertz, what you're going to find is that the electrons sit there and they oscillate, okay? So it turns out that we understand oscillating dipoles incredibly well. This is kind of a top view of what we were seeing there in the previous slide. This is, I guess, actually, yeah, so this is just the oscillating, and you see the dipoles re-radiate light. It's a little bit like sitting there and throwing a pebble into a lake, a smooth lake. You throw a pebble in, but it's periodic. So you throw a pebble in every once in a while, or you sit there with a stick and you bounce up and down on a smooth lake, and you will see these waves emanating. Well, like I said, we understand dipoles very well. And this is a picture of the radiation pattern from a dipole, right? And in this picture, the light is coming in along the x-axis here, right? And it induces a dipole moment at the center where there's an atom. So there's an atom at the center, point scatterer, we would say. And the electrons in that atom bounce up and down. And it turns out that the surface of a donut with actually 0 hole in the middle, it comes down and it converges right down to the nothing at the middle. That surface of the donut describes the intensity of the radiation, okay? So you could think of this, the red here, as the most intense scattering. And then in blue, there's no scattering. So if you put a detector, and we always use an eyeball for a detector, this is supposed to be an eyeball, and you look at some angle relative to the vertical here, you'll see that there's this donut-shaped radiation pattern, and it's given by sine squared of theta 1, where theta 1 is that angle between the observation direction and the z-axis. Okay, so looking straight down at the atom that's doing the scattering of the particle, you would see no scattering, and we can try to verify that in the lab. I don't think we always remember to do that, so if we forgot to do that, come see me and I will demonstrate that to you. You will definitely see that looking straight down on the scattering of most objects is absolutely nil. There's just nothing there. Okay, well, anyway, a better explanation of this appears in the AppTech book. This is actually your virtual book, chapter 14. You should be able to see something about that. This radiation pattern should be kind of familiar to you. It's like the icon that you see for wireless. So this is pretty well known, and you see that they say, well, there's not much scattering above the cell phone tower, you know. Okay, so let's stop at this point, and we'll continue up next time. We'll see how this parlays into scattering from gases, and then we'll work on liquids, which is incredibly simple at one limit anyway. And then we'll work our way after that onto polymer solutions. So we're going very stepwise. Thank you.